So we have the exercise laundry machine where we have the pipeline over the of the laundry machine. So for the first question, we have to make a sketch of the situation. It contains a pipeline, and in this pipeline we have a layer of sedimentation. The pipeline is given with blue lines, and the sedimentation, which is throughout the pipeline, is given with the red. The sedimentation has a thickness of a certain number. The pipeline also has a certain thickness D. Through the pipeline, water flows, so there's water flow through the pipeline given with the arrows. When you take a certain segment of this pipeline, and we take this little segment given with the green dotted lines, we have an arrow of sediment flow dissolving into the water with the solubility C star. Then for the second question, calculating K, we start by using the Chilton-Colburn relation. With the Chilton-Colburn relation, you have JD with Sherwood number divided by Reynolds number times Schmidt to the power of a third. This can also be rewritten to the following equation. This equation simplifies the equation for our situation. This JD is for mass transfer. Then for heat transfer, you have GH. And GH is Nusselt divided by Reynolds times Prandtl to the power of a third. And this can also be rewritten to the following equation. So this is also for heat transfer. What Chilton and Colburn say is that JD is equal to GH. And because JD is equal to JH, we can solve the equation for K. We can single K out and rewrite the equation, cancelling out the V's of the velocities and getting this equation. This can also be written, or the diffusion coefficient divided by the heat diffusion coefficient can be seen as Lewis number to the power of minus 2/3. So A is the thermal diffusion coefficient, and the D is the diffusion coefficient of the sediment. So we've got the formula for K. Now let's first calculate the Lewis number. So the Lewis number is A, the thermal diffusion coefficient of water, divided by the diffusion coefficient of the sediment. So A is 0.143 times 10 to the power of minus 6, and diffusion coefficient is 10 to the power of minus 9. This equals 143. Then filling in the rest of the numbers, so H is 10, then the density or rho is 2000, and Cp is 4.182 times 10 to the power of 3. And then times the 143 times to the power of minus 2/3. This equals in 4.372 times 10 to the power of minus 8 meters per second. Then, for the third question, we have to set up the differential equation over the thickness of the layer of sediment as a function of time. This means that we first have to make a mass balance. To do this, we need dm over dt. Well, there's no inflow, there is outflow, but there is no production. And as there's only outflow, you only have minus Vm, the outflow. This can also be written as minus A times Vm with two stripes as the flow. So A can be written as minus pi times the diameter of the pipe times the length of the pipe times K times C star minus C of the bulk, the concentration of the bulk, and C star is the concentration of the sedimentation. So the mass can also be written as volume times the density, and volume is the area times the thickness times the density of the sediment, and over dt. And this equals the same minus pi times diameter times length times k times c star minus c. Because rho, pi, the diameter, the length are not dependent on t, you can take them out of the d, the delta. This also means that you also can see that pi, the diameter, and the length fall away in the equation because they are on both sides. This means that the differential equation of the thickness of the layer of sediment as a function of time equals to k times c star minus c divided by the density. As the c is 0, as the bulk is so large that the sedimentation concentration is neglectable, c is 0. Therefore, you can rewrite the equation to minus k times c star divided by rho. For the fourth question, you have to use this equation because we have to calculate how long it takes for the layer to dissolve. So we take the equation of the last of question 3 and we look at the specifications. So at t is 0, the thickness at t is 0, the 0.002 meters. We have to therefore integrate the equation. So to integrate, we have to integrate the thickness from the thickness at t is 0 to the thickness at a certain point in time, and we have to integrate dt from 0 to t. Now solving the integration, you get thickness at a certain point in time minus this thickness at point at t is 0, and that equals minus k times c star divided by the density times t. Rewriting this equation, you get the thickness at a certain time is the thickness at a t is 0 minus k times c star divided by the density times t. Well, when everything is dissolved, the thickness is 0. So t equals the density times the thickness at t is 0 divided by k times c star. We have all the numbers in this equation, so we only have to fill it in. The density is 2000. The thickness at point t is 0 is 0.002. The k is from the second question is the 4.372 times 10 to the power of minus 8, and c star is 350. This equals in 261,403 seconds.